So you have graduated, or you have defended your master thesis, or you have concluded your doctoral. And then you ask yourself that question. Now what? Terrible question. That question should not be asked anyone from anyone. It's very hard to graduate and not seeing the future. Tomorrow looking unsure. Yeah, it's very hard. But you need experience to find a job. You need a job to get experience. That's a vicious cycle that one must get rid of. We here are not promising anything. We can't promising anything. But we can help you gather your chances for the petroleum industry. We can help you find ways to improve your chances to get in the industry, to fight for your job, for your place. This is what we want to do, to help you somehow. Well, many people don't agree with that, but there are many things in the engineering courses that are very useful in reservoir and petroleum engineering in general. They are really useful. Don't give up them. So you keep on studying certain tools, right? And thermodynamics. Thermodynamics is a very important and powerful tool in the day by day of a reservoir engineer. And we here are going to tell you some of these features that thermodynamics has to help you. We're going to teach you some tools that the reservoir engineers really use in their day by day. For example, suppose you have a huge, thick reservoir which properties vary only along depth, only in 1D, only along the Z direction. It is possible to show that now the chemical potential is influenced by gravity. All the thermodynamic properties are influenced by potential energy. And that's what's written here. d mu I equals to minus molecular weight of component I times g dz. Okay, so we can enunciate the classic problem of the isothermal compositional grading. The reservoir is already at thermodynamic equilibrium after millions and millions of years. And using the fugacity definition, we have RT d log fugacity is equal to minus mi g dz. Knowing pressure and composition at some reference level. What's a reference level? Well, for example, the one at which we collect the PVT sample, right? We want to know from this pressure and composition here, since we know the temperature which is uniform throughout the reservoir. Since we know pressure and composition at the reference level could be this one here, or this one here, this one here, okay? We can integrate this equation to know pressure and composition, to predict the composition elsewhere, upwards or downwards, whatever, okay? How much is this information worth? So you solve this nonlinear system of equations. You know that the fugacity at some other level, any other level, right, will be the fugacity at the reference level for which you know everything, right, times the correction of the gravity. And then you can calculate, you can do that for any other level you want. You can even predict the location of the so-called gas-oil contact. I mean the interface between the gas cap and the oil zone, if it really exists, obviously. So this is a simple system of equations that allows you to predict pressure in composition anywhere else along depth, since you know what's going on at the sampling depth, right? So there is hope. Thermodynamics is a fascinating subject, and it has multiple applications. We're going to talk to you about some of them in petroleum engineering. You can see that the Flash algorithm that you learn in your grad course. Do you remember the Rajford and Rice equations? They're really useful. Don't give up on them. The Flash algorithm is the fundamental basis of everything in this course. So you can get back there and review your notes. And then you see that the Flash algorithm is the fundamental basis of everything, but it's the very beginning to fit an equation of state based on PVT data. The PVT data, I mean mainly the differential liberation, right, is a series of Flash algorithm steps. And that's what we're looking for here. We're looking for some experimental data to fit the EOS. Have you ever used an equation of state in your day-by-day? It's time to do it now. It is really very useful. Not just equations, not just a truck of calculations. No, that's not true. They're very useful. Mathematical models with thermodynamics basis. They're very useful, but they must be fit. So fitting an equation of state is the starting point here. And the Flash algorithm is the basis for that. We must have the hydrocarbon extended composition. The petroleum reservoir fluid is a very complex mixture of hydrocarbons, and we must deal with that. We must learn how to classify them. We must learn how to model them, how to enter them in the reservoir simulation. We must expand and we must lump it. This is the very beginning. We want to get the reservoir fluid composition, the overall composition. This is where fun begins. Okay? We have the Flash. We have the overall composition. We have the experimental data. And then we fix our equation of state. This is the starting point. That's what I'm going to teach you here. It is really useful. Right? And then once you have your equation of state fitted, then you can perform compositional grading studies in 1D. And this will initialize and support your reservoir simulation. This is an application of thermodynamics, the main application of thermodynamics in the reservoir simulation. We'll use irreversible thermodynamics to do such studies. You use phase equilibrium under the gravitational field. Because some petroleum reservoirs might be 500 meters tall. Wow. 1 kilometer. And then gravity will play its role. So these are very important tools that you certainly have seen somewhere in the past. You will review it. You see that they are very useful. And you will learn here how to apply these tools to fight for your place, to fight for your job. in the petroleum industry. And then you ask yourself, now what? Well, but now you will be better prepared to fight for your job, to fight for your place in the petroleum industry by using the reversible thermodynamics tools on compositional grading calculation, by knowing how to calculate accurately the thermodynamic properties of a reservoir fluid using the fitted equation of state, you will be a kind of a differentiated employee. So, come with us, trust us, fight with us. Thanks. See you.